Okay, in this video on states of matter, we're going to continue taking notes where we left off the day before the test. So we talked about the difference between gases, liquids, and solids. The fundamental difference is the distance between the particles. One of the main things that has an effect on the distance is the strength of the attractions between the particles. Also the kinetic energy, which is similar. It's the kinetic energy, which is the 1/2 the mass times the velocity. You can think of the kinetic energy as somewhat analogous to the speed, but it's a little bit more than that because it also takes into account the mass. But it's the energy of movement, which is the correct way to think of it. So these two things take into effect how far the particles are apart. The words kinetic energy are the energy of movement, which is different from the energy of position. We talked and took notes on intermolecular forces. I call them intermolecular forces, but some people do call them van der Waals forces. We talked about one type of force, which is called a London dispersion force, which is the weakest intermolecular force. Every substance, whether it's polar or nonpolar, has London dispersion forces. And we did this example in class. This example indicate whether the following substances, octane or cyclooctane, would have these effects. We're going to talk about this in class on Wednesday. So we're going to start here. This is the second type of intermolecular force, dipole-dipole interactions. And a dipole occurs in a substance that is polar. So a substance that is polar, let's make this a little bit smaller. A dipole is an unequal distribution of charge. It occurs in a polar substance. In a polar substance, you have one side that is more negative and one side that is more positive. So dipole-dipole interactions occur between polar substances. Polar substances have permanent dipoles. The positive side of one polar substance will be attracted to the negative side of another polar substance. So we say the positive dipole of one substance will be attracted to the negative dipole of another. These forces are most important when the substances are pretty close to each other, because when you're really far apart, they aren't attracted. So these are instructions on how to determine polarity. You should be able to determine if a molecule is polar, because we just had a test on that, so I'm not going to go over this. So the more polar the molecule, the higher its boiling point. So here we're talking about how intermolecular forces, IMFs, have an effect on properties of substances. So this is the reason that we spend all this time learning how to determine if something's polar, because now we're going to use whether something's polar or not to determine the strength of its intermolecular force. Stronger intermolecular forces, IMFs, will have different effects on different properties. In this case, stronger intermolecular forces are going to cause a substance to have a higher boiling point, which is what it says up here, higher boiling point. That's because with the stronger intermolecular force, the molecules are held together, that the force is holding them together. Let's draw one. If this force, this attraction between these two different molecules, and I should have drawn it from one side to another, the positive side to the negative side, the stronger this attraction is, the harder it will be to separate them. So you need more energy to separate a strong attraction than a weak attraction. So the more polar the molecule, the more strongly this positive would be attracted to this negative, and therefore it will take more energy to separate them, which is why its boiling point would be higher. So in order to, we could take a look at this propane, CH3, CH2, CH3. I'm going to draw that Lewis structure for propane. I have 3 carbons, and in organic substances, they tend to draw out the order that the elements go to make it easier for you. So this looks like this. We have hydrogens here. Now tell me, does this look polar or nonpolar? If you said nonpolar, you are correct. This is a pretty nonpolar molecule. All of these carbon-hydrogen bonds, if you check their electronegativity, are going to be close to nonpolar. The difference is less than 0.4. Plus, they're pretty balanced. Here, you have a nonpolar bond because it's carbon to a carbon. So this is a pretty nonpolar molecule. So look at its boiling point in Kelvin. Its boiling point is 231 in Kelvin. I'll remind you, Celsius, 0 in Celsius, 0 degrees Celsius equals 273 Kelvin. So in order to find a Kelvin temperature, we have to add the we have to subtract from Kelvin. We would subtract 273 to get the Celsius temperature. So 231 minus 273 equals something, 42 degrees, minus 42 degrees Celsius, I think. Let's check that. That is correct. So the boiling point for propane is minus 42 degrees Celsius. Now we'll look at this one in the middle, methyl chloride. I knew that was going to happen. I'm going to just leave that there, move this off to the side. So methyl chloride is, carbon with 3 H's and 1 chlorine. So here we have 3 nonpolar bonds, I'll draw them black. We have 1 polar bond pointing towards the chlorine. So this is more polar. Whoops, didn't mean to erase that. How do I go back? Does that do it? Sorry. This is more polar than this, meaning that the attraction, this is going to be the negative side of this molecule. So this might be attracted to the hydrogen side here of another one. I'll draw an attraction. So the energy to break this intermolecular force will be greater than the energy to break an intermolecular force here, because this is basically just going to have London dispersion forces, very weak attractions. So the boiling point of methyl chloride is 249 Kelvin. Let's change 249 Kelvin to Celsius. 249 Kelvin minus 273. It's going to be a little bit higher than negative 42. It's still going to be a gas at room temperature. Oops. 249 minus 273 is negative 24 Celsius. And acetonitrile, you can tell just from looking at the formula before I scribbled over it, is going to be even more polar, and its boiling point is 355. 273. I think, am I doing this backwards? No, I'm not, but what's going wrong? Right, never mind. 355 minus 273 gives you a boiling point that's above 0. 355 minus 273, 82 degrees, so above room temperature. So this acetonitrile should be a liquid at room temperature. So to convert from Kelvin to Celsius, you take your Kelvin temperature. Kelvin minus 273 equals your Celsius temperature. Okay, we're going to talk about this in class. Now we're going to skip word and talk about hydrogen bonding. Hydrogen bonding, which so this is some data And if you look here, we're going to look from tin, where this is group 14. This is group to carbon. So we have tin with 4 hydrogens. We're going from, which way should we go here? Let's go from smaller to largest. So here we have CH4, methane, looks like this, with hydrogens at the end. This is pretty nonpolar, so your major force will be London dispersion forces. These are all going to be pretty nonpolar because you have 4 hydrogens around 1 atom. And as the molecular weight increases, your London dispersion forces increase, so that makes the boiling point, I think is what we're measuring here, go up. As the molecular weight goes up, the London dispersion forces, the LDSs, increase because the molecule is bigger, and therefore you need more energy to separate them from a liquid to a gas phase. Here, these are polar molecules in the red line. We have, this is group 16, the red is group 16. And in each case, well, if you start here, this is sulfur with, and it's going to be polar, sulfur with 2 hydrogens and 2 lone pairs. They're all going to have the same structure. I'll circle. This will have a larger molecular weight because tellurium is bigger than sulfur. This one's in the middle. So these 3 follow a trend. The boiling point increases slightly as molecular weight increases. But this tiny molecule, which has a very low molecular weight, only 18 grams per mole, or 18 atomic mass units per molecule, has a very high boiling point. So this is strange. This is not following the trend. Why is that? The answer is something called hydrogen bonding. Hydrogen bonding is a type of dipole-dipole force, and it is a very strong type. So it is very strong, special dipole-dipole force. It only occurs when hydrogen is bonded to nitrogen, oxygen, or fluorine. And where it occurs, if hydrogen is bonded to, these are 2 different molecules. This is a water, and this is a water. And the red dots here, those are your intermolecular force. So what occurs between the oxygen in one molecule and the hydrogen that is bonded to an oxygen in another molecule. So two things. The hydrogen has to be bonded to a nitrogen, oxygen, or fluorine. And then the force occurs between the hydrogen that is bonded to that oxygen, nitrogen, or fluorine and one of those 3 atoms in another molecule. So you can see that here. Well, actually, so here we have hydrogen bonded to an oxygen, and the hydrogen bonding is occurring between the hydrogen that's bonded to that oxygen and a nitrogen, which is one of these 3 special highly electronegative molecules in another molecule. So this is a special type of force that we need to understand pretty well. I'm going to stop this video here, and then we're going to talk about this in class as well. The next video is going to talk a little bit, well, let's just do one more slide. Okay, I think I said this already. Hydrogen bonding arises in part from the very high electronegativity of nitrogen, oxygen, and fluorine. And that exposes the hydrogen nucleus, which is positive. And we're going to talk about this some more. So next video, we're going to talk briefly about ion dipoles, and then we're going to talk about how these intermolecular forces affect properties, and then there will be a 3rd video on phase changes.